Part D, brute force method. D.1, introduction to brute force method. All right. First, description of brute force method. Yeah, the properties of brute force method. Yeah. So it's a straightforward approach. Yeah. So usually people, yeah, especially when they do not have any idea, when they work on a computing problem, some problem relatively hard at the beginning, they may not have any good idea. Yeah. So the first thing they can try a straightforward method. Straightforward, usually it means you do not apply any special technique. Okay? Yeah, just work on the data directly. Yeah. All right. Yeah. Because in that way, you can always apply it to a problem. Yeah. Usually it's not good, but you want to get some experience. Yeah. So when you work on it, you try to find some special property and they try to take advantage of those properties. But you need to put your hands on it. Yeah, try to, play around. Yeah, try to, get some experience. Yeah. In general, it is not the best algorithm. Yeah. In general, especially when the problem is relatively hard. So if you use the brute force way, you cannot get the best solution. Otherwise, the problem is easy, right? Think about it. So if you use the brute force method, you can still get the best solution. That means the problem is very easy. Yeah. So it is usually used as the starting point for more advanced algorithms. Yeah. So actually you use it as some, building up your experience. And you use this experience to help you understand the problem better. So it's an understanding process. So you treat this simple method as the understanding process for a relatively hard computing problem. Yeah. The efficiency difference between the brute force method and the more advanced algorithm could be huge. Yeah. Right. So later you need to improve your algorithm in several rounds. Okay, yeah. After you get a satisfied solution, satisfying solution, yeah. So then, if you compare it with your early brute force method, you can find a big difference. Yeah. All right. But sometimes still useful. Yeah. So sometimes, so we use this early stage to help us understand the given problem. Yeah. All right. Yeah. So we can use our polynomial evaluation problem. Before we learn that Horner's rule, that's the brute force method. Yeah. And after we learn Horner's rule, we compare their efficiencies. You can see the efficiency difference is huge. Okay. Yeah. In our one special example, we get a huge difference like this: 5.8 days versus 1 second. That difference. Okay. Yeah. All right. Now, sorting array problem. Yeah. All right. Yeah. Because the first time we did, the first time we did that selection sort, right? Selection sort. Yeah. So for the selection sort, we know it's not an efficient algorithm. Yeah. So we can do improvement many, many times. Yeah. Here, our second time to do the sorting, but this time we try to use different properties. Yeah. So we need to do our observation another time, and we try to find a different property. When we use different property, we can find a different algorithm. Yeah. All right. So given, the same problem, yeah, but this time we, yeah, so we try to, yeah, so we do not use our old view, yeah, because if you use the old view, you get an old algorithm. So we want to completely change our view. They completely change our view, yeah, different view. Yeah. All right. So you may ask this question, why we need to solve it another time, right? Yeah. We already solved it. So one answer is because the old solution is not good enough. So we want to improve it. Okay. Yeah. But in general, yeah, in problem solving, some of the problems, even if we find a good solution, sometimes we need to find other different solutions. Yeah. So here from the problem solving point of view, yeah. So let me answer this question from the problem solving point of view. Yeah. So why we need to solve it another time. Yeah. So our view, a problem is a carrier of a set of thinking methods that result in different solutions. Yeah. So let me explain this. Yeah. When we solve problems, we use different ideas, different methods, different strategies, different techniques, right? Yeah. And those methods, techniques, thinking, manipulations, those things are valuable, right? Yeah. Those problem-solving tools, techniques, they are valuable. Yeah. And we, in the future, we want to use those methods, techniques to solve many different computing problems. But the thing is, how to carry those techniques, methods, tools, how to carry them, okay? They are not concrete objects, right? The techniques, methods, those things, they're not concrete objects. So you can carry, you put in some box, you can carry. So it's not that, okay? So they are, thinking things, yeah. They're thinking idea things, yeah. So we imagine we use our specific problems to carry different solutions for one particular computing problem, to carry those different methods, techniques, thinking, manipulations, those things. Okay, yeah. For example, in our sorting algorithm, yeah. Let me go back to you, Madison. Yeah. So, for example, in our sorting algorithm, yeah, we have several different thinking methods. Yeah. Later, we have a few more solutions. Yeah. So you will see. So we apply, different techniques. Yeah. Many of them very tricky, very smart, yeah, very valuable. in our future problem solving, all those methods could be very useful. Yeah. But yeah, think about those abstract things, those ideas, how to carry those ideas, right? It's hard to carry those ideas, right? Yeah. Although you can write on a paper, but how do you keep that paper? You can put on compute, store as a file in your computer, but how do you keep track of that file, right? Think about it. It's not easy. Yeah. Now, so here, a simple way, right? So our sorting problem, the sorting problem, we know there are 6 different solutions. So if we are well familiar with those 6 different solutions, those 6 solutions carry 6 different methods. Yeah, so if we were familiar with that, so then in our future problem solving, we just recall our sorting problem, the 6 different solutions for the sorting problem, we can recover those techniques. Yeah, something like this, okay? Yeah, all right. Yeah, so medicine, so like phrasing the question in different ways can help change. Yeah, here, different. Yeah, phrasing question different. Here we have the same question, right? Sorting. We do not change its representation, even phrasing. We're phrasing the same way. Yeah, but solutions are different. But the different solutions based on different views, different properties, different, techniques, understanding, different understanding. So now phrasing, because when you do different phrasing of one question, you change your wording, but the fundamental things you do not change, right? That's what we call rephrasing, right? Rephrasing. You do not change the fundamental properties, yeah. So, but you change different expressions. Yeah, but here it's different. Okay, yeah. Right. Yeah, different phrase. Yeah, here yeah. So I would like to represent your sentence here in a different way. So phrasing the question in different ways. Here we're not phrasing. Here we view this. So here we use different views to look at this question. Yeah, not phrasing, because phrasing we treat as some superficial thing. Yeah, not a fundamental thing. Superficial. Okay, phrasing. Yeah. Change some skins, just like change some skins. The meat is the same. We only change the skin colors, or that kind of thing. Here we use totally different views, totally different understanding. So we even change the meat part. We change the meat part to get different solutions. Okay, yeah. All right, so let me end my explanation at this point. Yeah, so let's continue our solution part. Yeah. All right. Yeah, the thinking methods are important to help us solve other problems. Yeah. So the most valuable, most important things, the thinking methods, the working techniques, the tools, those things, those knowledge items, those things, very important. Yeah, so that's what we like to learn. Yeah. All right. Now, go back to this particular question. I want to show you how to change our view. Completely different view. So we need to discover a different property. Okay, yeah. A view based on a special property. Yeah. So let's look at this question in a different property. So let's do observations. Yeah. We need to find that property first. Yeah. So then we would design our algorithm based on that property. Yeah. So that's the understanding part. Yeah. All right. let's look at this diagram first. So this is a given array. Okay. Now, in order to sort this array, we consider the order information, right? Yeah. Ascending order, descending order. Our goal is the ascending order. So that tells us we need to study the order relationship among different elements. Yeah, that's our new view. Okay. Yeah. Although our new view is related to our old view, but we like to understand in a different way. Okay. Yeah. All right. Let's look at arbitrary two elements in this array. Okay. Yeah, we just want to compare two of the elements in this array and look at their order information between these two elements. Yeah. Here, a sub I and a sub I plus 1. Yeah. Think about if they are in ascending order, then we do not worry about it, right? Yeah. If these two elements are already in ascending order, then we can move to another two elements, right? But if they're out of order, yes, we worry about the case when these two elements are out of order, not in order. No, not in the order we like to have. So out of order. If out of order, we need to fix it, right? Before we move to the next pair of elements, we want to fix this out of order problem first before we move to the next pair. Right? Yeah. Fix it. Okay? Fix it. We can do a swap operation to fix the order problem, right? Yeah. Out of order, that means the first element is greater than the second element. How about we just swap these two elements? Then we fix the order problem. That's our new understanding, our new view, new property. We didn't use this way before. Okay, yeah. So this is our new view. Yeah. All right. So now here is the observation for critical property related to the order information. If the array is not sorted, there must be two adjacent elements that are out of order, right? Think about this observation. Can you get this property? Understand this property? There must be two adjacent elements that are out of order. Otherwise, let's do the negation of this statement. Negation. Otherwise, if there is no two adjacent elements are out of order, that means any two adjacent elements are in order, can we say the whole array has already been sorted? Yes, any two adjacent elements are in order, are in ascending order, right? By the transitivity, we know the transitivity property, right? Yeah. After we apply the transitivity property, the whole array must be ordered. Okay, but the condition here, if the array is not sorted, we have this condition. That means there must be, we can find at least two adjacent elements that are out of order. Okay, yeah. So that's the critical property we discovered. All right. Now we want to explore this property to find a solution based on this observation. Yeah. All right. Yeah. Because Out of order, we want to fix it. We want to make them in order. We just do a swap operation, then we fix it. So that's our solution. That's the basic step of our solution. Okay, yeah, all right. Yeah, here I give you the reference in the textbook, section 4.1. Yeah, all right. Now, in order to do a complete discussion based on this observation, this property, we want to learn a new concept, inversion concept. We need to define the special concept, inversion concept. Okay, yeah, all right. So what is an inversion in an array? A pair of elements, A sub I and A sub j, is called an inversion. Then they must satisfy this condition. If I less than j, the subscripts I less than the subscript j, but their values are in different order. The value order and the subscript order are different. A sub I is greater than A sub j. That's the value order. Value order is opposite of the subscript order. So we call that inversion. Yeah. Out of order, so we use this inversion concept to describe that out of order phenomena. Okay? Yeah. So there, after we have this concept definition, so we can describe our property in a newer version. Yeah. All right. Yeah, let's write in this one. If the array is not sorted, there must be an inversion, right? Can you see that? Yeah. Here the inversion, so it's different from our critical property. Critical property, we require two of the adjacent elements. And here, we just say inversion. Yeah, not necessarily this inversion happens between two of the adjacent elements. This inversion could happen between any two elements in the array. Yeah. So here our statement is, if the array is not sorted, there must be an inversion. Right? Yeah. Because you can use the contrapositive method. If there is no inversion, think about it. If there is no inversion in an array, then the whole array must be sorted. The whole array must be in ascending order, no inversion. If you can find one inversion, it is not sorted. It is not in ascending order. That's very simple. Yeah. All right. Yeah. So this is one property, yeah, we can find in an array. Okay. Yeah. Then another one. Yeah. So this is the first version property. So now we want to write another version of the property. Yeah, equivalent property. So the second version is, if the array is not sorted, there must be an adjacent inversion. An adjacent inversion. So this second statement, the same as our above critical property, that one, because adjacent two elements. Yeah. Yeah. So you can see the bottom two statements are equivalent. If the array is not sorted, there must be an adjacent inversion. See, the wording is different. Look at the wording of these two statements are different, right? The first version, there must be an inversion. Here, the inversion, we mean a global inversion. The two elements selected from the array that form an inversion is a global inversion anywhere in the array. So it's a global view. Okay. But the second adjacent, it's a local view. Local in, we are only interested in adjacent inversion. In the second version, we're not interested in the global inversion. Okay, yeah. But why we prefer the second version than the first one? Because the local inversion is much easier to fix than the global inversion, right? Global inversion, you need to look everywhere in the array. So you need to do more work. But for the local inversion, you only need to, every time you just look at the two adjacent elements. So you can do less work. Think about that, okay? When you do less work, you can improve your solution. You can reduce the cost of your algorithm. Yeah, so we prefer the second version, the adjacent inversion. Okay, yeah, all right. Yeah, so there, based on this understanding, so you can see before we really do our solution, we try very hard to understand the problem. We spend a lot of time to understand the problem, like this, you know, observation, discover the properties. Okay, sometimes we need to define some concepts. Yeah, all right. Now let's look at the solution, how to fix it. I mentioned before a swap operation, right? We just do a swap operation. We can fix one inversion. We can reduce that. We can eliminate that given inversion by a swap operation. Okay, yeah. Implementation idea. Yeah. Our goal, we want to remove all the local inversions by local swaps. Yeah. So if you can implement this idea, you get the array sorted. If you can remove all the adjacent inversions, you get the array sorted. That's our new view, our new method. Okay, yeah. So let's complete the implementation details. Yeah, all right. So we do in this way, the procedure. We start from the first element for each scan. So we scan the array, but we need to scan multiple times, yeah, until we get the whole array sorted. So the first scan, we start from the first element, yeah, and we compare every two adjacent elements moving to the right, from left to right. Okay, yeah. If we see one inversion, then we do swap operation. If we do not see any inversion, we move to the next adjacent pair of elements. Yeah. All right. Step 2, do swaps one by one from left to right when necessary. Sometimes we do not need to do, right? If necessary. Yeah. Sometimes those two elements are already in order, so we move to the next two adjacent elements and so on. Okay, yeah. Step 3, stop at the first in-place element. Yeah, because when you do this kind of operation, you will see you always put the last element in place. The last element, yeah, the last element, that's the largest element in the array. You always put the last element in the array in place. Yeah, because when you have the last element in the array, every time when you compare two adjacent elements, this last element will cause an inversion. So you need to swap it. After the swap operation, you get that last element, largest element. So you still need to compare that largest element with the next element. Another swap operation, you still need to compare until you reach the end of the current array. That's the final position of this element. That means you put it in place. So every scan, you put the largest element in the current array in place. Okay? But your second scan, you do not need to touch those elements already in place. Okay? Yeah. The second time, because if you put one element in place, you do not need to work on it anymore. It's already in place. Okay? So you only need to work on the remaining elements. Yeah. All right. So here you can see, based on this procedure, yeah, the property. Yeah. Based on the procedure, so we can see some property. Yeah. So the first property, there is one element in place for every scan. Yeah, that's the largest one in the current array. Okay, yeah. So you move it to the rightmost position. Yeah. That's the in place location. Yeah. The in place element of each scan appears at the end of the current array. Yeah. The largest one, it's at the end of the array. Yeah, the second property. Yeah. All right. The current array is a subarray that excludes all the in-place elements. Yeah. So because those elements already in place, you do not need to touch them anymore. Yeah. Leave them there. Yeah. In that way, you can reduce your problem size. Every scan, you can reduce your problem size until you finish the last scan. Okay, all right. So that's the new algorithm. And this algorithm here, based on the visual imagination. Yeah, so this procedure, we try to visualize. So the visual imagination, the swab looks like a bubble moving to the right, from left to right. Yeah, so that's the bubble sort. So everyone knows the bubble sort, right? In our CS3250, we learned this bubble sort before, right? Yeah, so CS3250, we learned this bubble sort before. And in many programming language, actually, this bubble sort is implemented in many programming languages. Yeah, so you have some experience. But here in our discussion, we try to work on it based on our understanding of the problem solving. Yeah, because when you learn this bubble sort before, you didn't learn that inversion concept, right? Yes, yeah. And you didn't follow our typical problem-solving procedure, the thinking, the view, the analysis, the understanding. Yeah, you didn't go through those basic steps. Yeah, here I use this, our old example. This is an old example to try to show you some basic problem-solving steps. Okay, yeah. All right, so yeah, this is the bubble sort. All right, yeah. Efficiency analysis. After we know the solution, we need to look at the efficiency analysis. How many comparisons do we need? How many comparisons Here, based on the solution description, you can see we do a lot of swap operations, right? Yeah, we do a lot of swap operations to fix the inversion problems, the inversion problem. Yeah. So the question, remember, we learn a concept. Yeah. We learned a concept before, the basic operation concept. What is the basic operation in this bubble sort? Yeah, basic operation. Yeah, the operation that contributes the most in the running time, response time. Okay, yeah. Here you can consider two different types of operations. One is swap operation, another is comparison. You need to do comparisons, right? How do you know you have one inversion? You need to compare the values of two elements. Then you can see if they form an inversion or not. So you need to do a comparison. So which one should be the basic operation, swap operation or comparison in bubble sort? Think about that. Which operation contributes the most in this algorithm? So you do most frequently in your implementation of the solution. Basic yes, answer is comparison, not a swap. Okay, yeah, the answer correct. It's comparison, but not swap. Yeah, Madison explained, well, you have to compare every time. Right, yeah, here, yeah, let me explain. Yeah, so here we need to compare the swap and the comparison. All right, only, let me say in this way, only when you discover an inversion, you do swap operation, right? When you do not encounter an inversion, you do not do swap operation, right? But every time you want to check if there is an inversion, you need to do comparison, right? Yeah, think about it. Yeah, so let me say in this way. If the array is already sorted, yeah, the input is already sorted, then there is no swap operation, right? Because every time when you check if two adjacent elements form an inversion, they are in order, no inversion, so you do not need to do swap. But you need to do comparison, right? When you check if two adjacent elements form an inversion, you do one comparison. So you can see you do comparison more frequently than you do swap operation. Okay, yeah. So that's the reason comparison operation is the basic operation. Yeah. So here, when you do efficiency analysis, you should count the number of comparisons, not the number of swaps. Okay, yeah. All right. So yeah, so the answer comparison. Okay, yeah. All right. And so here we do not do explicit efficiency analysis here because the result is very similar to the one in the selection sort. The best case, worst case, very similar to that selection sort. Okay, yeah, when we count the number of comparisons, yeah, the same number as in the selection sort. Yeah, yeah. All right. But yeah, here, before we move to the next topic, yeah, let me say one more word, a few more words. So when you count the number of comparisons, the selection sort and bubble sort, they have the same number. Okay, yeah, it's the same number here. What I mean that 1/2 times n minus 1. Okay, so this is true for both selection sort, selection, and the bubble sort. Okay, yeah. But there is a key difference part. So if you compare, so you can compare the swap operation. Swap operation. How many swap operation? Okay, yeah. And in the selection sort, you can see you do swap operation much less than you do in the bubble sort. We do not do a lot of swap operation. Think about. Yeah, yeah. In selection sort, because we find the minimum, right? Find the minimum. Yeah. So every scan, you find the minimum of the current array, then you do one swap operation to put that minimum in place. That's every scan, you only do one swap operation. But in the bubble sort, in one scan, we do many swap operations, right? We do many. Usually, we do many swap operations. Yeah, but in the selection sort, we do at the most one swap operation. That's the difference. Yeah. So the same number of comparisons, but swap operation, selection sort is much less than the bubble sort. Okay. Yeah. Yeah. All right. So let's